Okay, lesson 1.1, functions, domain, and range. So we're going to talk about the difference between just a general relation and an actual function. Okay, so up until now, we called a lot of things relations. So like the relation of a line, the relation of a quadratic, or like a quadratic relation. Okay, but now we're going to go into further detail. A relation is an identified pattern between two variables. So very general, okay, that may be represented as ordered pairs, which is x, y, okay, table values, a graph, so you can have something going on, or an equation, y equals something. Okay, so this is in general. A function is more specific. A function is a relation in which each value of the independent variable, so like the first coordinate, which is usually the x, corresponds with exactly one value of y. Okay, and we're going to get more into this. So please note all functions are relations because, again, function is a more specific one, so all functions are relations, but not all relations are functions. For a relation to be a function, there must be only one y value that corresponds with a given x value. Okay, so let's do an investigation. Are the following relations or functions? Okay, complete the following table of values for each relation. So, y equals x squared. Well, we've seen this before. This is quadratic. So, negative 3 squared, negative 2 squared, negative 1 squared, 0 squared, 1 squared, 2 squared, 3 squared. Okay, so that's easy. So when we look at coordinates, we're looking at negative 3, 9, negative 2, 4, negative 1, 1, 0, 0, 1, 1, 2, 4, 3, 9. Okay, now I did this one a little bit backward on purpose though. Let's look at x equals y squared. So we're actually solving for the x value, which is backward. You won't really see this. This is just an investigation. So you won't see this very often. But what we're going to do is we're going to take whatever y we get and we're going to square it. So negative 3 squared is 9, negative 2 squared is 4, negative 1 squared, 0 squared, 1 squared, 2 squared, 3 squared. So this time the coordinates are just backwards. 9, negative 3, 4, negative 2, 1, negative 1, 0, 0, 1, 1, 4, 2, 9, 3. Okay, and let's go ahead and graph those. So we have negative 3, 9, negative 2, 4. Okay, this is our normal parabola. That's great, y equals x squared. Now, let's graph this one. So 9, negative 3, 1, 2, 3, 4, negative 2, 1, negative 1. So as we can see, this is just like a parabola, except for it's on its side. And we're actually going to study this year. So this is y equals x squared, or x equals y squared. Okay, so now let's talk about what a function actually is. We're going to go ahead and do C. We're going to draw vertical lines at negative 2, negative 1, 0, 1, and 2, okay, on both of these graphs. Okay, so negative 2 on this graph doesn't go through the graph, that's okay. Negative 1, 0 goes through it this one time, and then we have 1 and 2. Okay, these two here are the important ones. Okay, so for y equals x squared, every single time we drew a vertical line, it hit the graph one time. Now, every single time we drew a vertical line in x equals y squared, well, negative 2, negative 1 didn't hit the graph, so those ones actually don't matter, okay? They don't tell us anything about the graph. 0 hits it once, which is good, that's still a function, but the more we go up, now, when we drew a vertical line through 1, it hit the graph twice, and 2 hit the graph twice. Okay, so we call this the vertical line test. Vertical line test, where if we can put a vertical line through a graph and it only hits it once at any single point, then this is a function. The fact that at 1 and 2, our vertical line hit this graph twice, this is not a function. And that's because each one of these independent numbers, so for example, 1 doesn't just have one dependent number. It actually has two. It would have 1, 1, and 1, -1. So there's our issue. So formally, the vertical line test is a method of determining whether a relation is a function or not. If every vertical line intersects the relation at most one point, then the relation is a function. Okay, here are two examples. So the first example here, this graph passes the vertical line test because when we draw vertical lines anywhere through this graph, it at most hits the graph one time or intersects it one time. Okay, the second one, which is a circle, this fails the vertical line test because a vertical line intersects the graph at more than one point. So at some points, like for example here, it may pass the vertical line test, but we need to check the vertical line test holds for every single vertical in that graph. And in this case, it fails because it passes through twice. Okay, so example 1, use the vertical line test to determine whether each relation is a function or not. So when we go vertically here, it always passes just once. When we go vertically here, we notice that multiple times it passes the graph more than once, so not a function. Go vertical here, passes once, so this is a function. Vertical here, it's passing more than once, multiple times, not a function. Now, domain and range. Okay, for any relation, the set of values of the independent variable, so often called x values, is called the domain of the relation. So these are values that x may take on. Okay, and the range is the set of corresponding values of the dependent variable, often like the y values, and this is called the range. Okay, in general, there's a general notation for the domain and range. Usually we rewrite it as one of these two things. So we can either have a discrete function or a continuous function. Okay, a discrete function is when it lists x, y values. A continuous function is usually when it gives us an equation. Okay, for a discrete function, we want to actually put a squiggly bracket, x, this is an e, it represents element of, and then the r is the real number system. So x is an element of the real number system. This slanted forward line means such that x equals, and then you list every number that x equals. Likewise, the range, y is an element of the real number system such that y equals, and then you list the numbers that y equals. Okay, for a continuous function, a lot of times we use, like I call the crocodiles. Okay, so x is an element of the real number system such that this just represents like x is between this lower number. Let me delete this. Okay, so this one is going to be the lower number, and then this one is the higher number. So maybe x is between 2 and 10. Okay, same thing for y. Y is an element of the real number system such that y is between, say, -10 and 45. And please note, for a function, for each given element in the domain, there must be exactly one element in the range. Okay, so let's scroll down a little bit. Okay, so just going back to what a real number is. So a real number, and it's usually like with a double line and an R like that, okay, it's basically any number that we're going to deal with in like probably up until like first or second year university, Okay, so the only number that it doesn't include is something called the complex number, which is like this, and you won't see that. But this is basically any integer, any decimal that like stops, so for example, 0.25, any repeating decimals, okay, any non-terminating decimals, maybe like pi, it just keeps going, and any non-repeating decimals, okay? Oh, non-repeating decimals would be pi, okay? Non-terminating decimals, it just keeps going, okay? So basically any number that we deal with, this is like the real number system, so that's why we use that. Okay, so let's go example 2. Determine the domain and range of each relation from the data given, then state whether the relations are a function or not. Okay, so domain is going to be D colon, and we're going to do a squiggly, and range is going to be the same idea. Okay, R colon squiggly. So we have X is an element of the real number system such that, now both of these examples are a discrete, so we have to just list them. X equals -3, we'll put them in order, -2, 5, 5, and 6. So we don't have to write 5 twice. Okay, and then squiggly bracket to end. The range is Y is an element of the real number system such that Y equals, now we just list them, and smallest to largest. So -8, -6, 3, 4, 7. -8, -6, 3, 4, 7. Now, let's determine whether or not this is a function. So I see that there's a repeating X here. And this means that like if we graph this, we'd have like 5 and -6 somewhere here, and 5 and 3 somewhere here. And if we put a vertical line through this, it would not pass the vertical line test. So this is a relation, not a function. Okay, let's do the next one. We have domain and range. That's how we set it up. Domain colon squiggly bracket. X is an element of the real number system such that X equals 4, 5, 6, 7, 8, 9, 10. 4, 5, 6, 7, 8, 9, 10. Okay, Y is an element of the real number system such that Y equals, let's put them in order, 5, 8, 9, 11, 12. 14, 22. Now, looking at the ages, which is like the independent, none of them repeat, okay? Therefore, this is a function. Okay, example 3. We're going to determine the domain and range of each of these relations. These are going to be continuous because we're given a equation, and then we're going to state whether or not it's a function. Okay, so for example, y equals 2x minus 5. This is a line with the slope of 2 and the y-intercept of -5. It's -5, and it goes like this. Okay, so this is going to be a little bit different. The domain is going to go left and right forever. See how it's going to the right forever and the left forever? So all we do is XER. That means X can be any number. You can take any number, you can sub it into this X, and it's going to yield an answer, okay, a Y value. Now, range. Going up, it's going to go forever. Going down, it's going to go forever. So YER. Okay, and then this one's done. So this is a function. Okay, the next one. This is going to be a parabola with the vertex at 1, 3. And this is going to open up because it's positive A. Okay, so for the domain goes left and right. It can go to the right and it can go to the left no matter what. So we're just going to go XER. Now, we said that the vertex is at 1, 3. So when we take a look at the numbers of the y-axis for the range, we know that the parabola kind of starts at 3 type of idea and goes up. So in this case, all of your y values are going to be equal to or greater than 3. Okay, if it opened down, it would be less than that number. And yes, this is a function. Okay, I'm going to show you what this looks like. So this is a root function, and I call it a pretend vertex. So it's not actually a vertex, but it's kind of where our root function starts. And the base root function looks like half a parabola. It's going to start at 1, 3 again, okay? So it's going to start here, and it's going to go over like this. So it's going to go up forever and to the right forever. Now, the domain is going to be XER, such that, so x is going to start at 1 and go to the right. So x is going to be greater than or equal to 1. Okay, and the y values, again, this is going up and down. We can start it with y as an element of the real number system, such that y starts at 3 and goes up. So y is greater than or equal to 3. Okay, this passes the vertical line test, so yes, it's a function. Okay, we're going to study this one as well. X squared plus y squared equals 36. We studied this last year in grade 10. This is a circle with radius 6. So the numbers for the x, I'm going to drop the d. Okay, so x is an element of the real number system such that, so the x's occur between -6 and 6. Okay, and the y's again occur. The lowest y is -6. So y is between -6 and +6. And yes, this is a function. Okay, I'm going to tell you what this looks like, but you can also do this algebraically. We're going to study this. Okay, algebraically, we cannot have a 0 in the denominator. So x plus 3 cannot equal 0. Okay, so x cannot equal -3. So at -3, this actually has a vertical asymptote. So again, we're going to study this year, but at -3, this is not going to exist, and then at 0 as well. Okay, so this is a little bit different. X is an element of the real number system such that x does not equal -3. And we can just leave it like that as one restriction because x is going to equal every single number forever. Okay, it goes left and right forever, but it's not going to equal -3. Okay, and y is an element of the real number system going up and down. Y is not going to equal 0. And yes, this is also a function. Okay, it passes the vertical line test. Sorry, I'm going to take this back. This is not a function. Okay, when we do the vertical line test on a circle, it does not pass. Okay, and a recall from grade 9. So vertical lines take on the form x equals x-intercept. We're going to need this for this course. And horizontal lines take on the form y equals y-intercept. So when we're dealing with vertical lines, a lot of times in this course, we're dealing with asymptotes. So what is an asymptote? It's a line that a curve approaches more and more closely, but never touches. Okay, so in the graph to the right, there exists a vertical asymptote at x equals 3, and this is obviously labeled in the red. And there's a horizontal asymptote at y equals 0. So this graph comes closer and closer, both ways to 0 and then up and down to 3, but it never touches it. So for example, it could be like 3.0000000 all the way 1, but it's never actually going to hit 3. Okay? In the graph on the right, there exists a horizontal asymptote. So this is another function that we're going to be dealing with this here. So this becomes closer and closer to -2, but never actually hits it. Vertical asymptotes affect the domain, whereas horizontal asymptotes affect the range. Okay, so division by 0 is undefined, therefore an expression in the denominator of the function cannot be 0. So I'm going to show you this like in real form. So if we have an example like from the previous page, y equals 1 over x plus 3, we already talked about how we cannot get y equals 1 over 0. Okay, this doesn't exist. So in order to get like that 0, what would be the restriction? We'd have to sub in -3 to that bottom, and then we would get the 0. So that would be the restriction, and therefore x cannot equal that -3. Okay, and there's a vertical line at -3. Now this one's a little bit more complicated. Okay, a lot of individuals understand that we cannot get 0 in a denominator, but this one, for the range, there can never be a situation where the result of a division is 0. So for this equation, y equals 1 over x plus 3, if we actually subbed in the 0 equals 1 over x plus 3, here's the thing. We can cross multiply this x plus 3. If it cross multiplies, we get 0 equals 1. Well, does 0 equal 1? No, 0 can never equal 1. Okay, so 0 can never equal 1, and therefore there's a horizontal line at y equals 0. Okay, for all functions where the denominator is a higher degree than the numerator, there will be a horizontal asymptote at y equals 0. So let's just show the domain and range algebraically for this equation. So we know that for y equals 1 over x plus 5, we know x plus 5 cannot equal 0. So we bring over that 5, x cannot equal -5. So that's pretty much our domain. So we can say domain is XER such that x cannot equal -5. X can equal any other number, just not -5. Okay, so there's a vertical asymptote at -5. Now range, 0 equals 1 over x plus 5. Here's the problem. We cross multiply, we get 0 equals 1. That can never be. So there's going to be a horizontal asymptote at y equals 0. So therefore, the range is YER such that y does not equal 0. And that's how we show that algebraically.